Hello and welcome to this session of the course Elements of Mechanical Vibrations. In the previous session, we discussed the modal analysis approach to an undamped vibratory system and explored the way of finding out the free vibration response to initial conditions. Having discussed this, let us now understand how the same is extended for a damped vibratory system and what changes are required to be made if we are to get the response estimated. Now, let us look at damped free vibration. And the process is going to be quite similar, okay, except that there would be some twist and turn. All right, so how did we write that for a typical multi degree of freedom system? You had a damping matrix now, right? And you can find how to get that damping matrix. You still consider forcing function to be 0. Now, again the transformation and pre-multiplication will give you this. I made a small mistake here. Need to set it back to. There is no problem with this. There is no problem with this. We already have shown them. Practical systems would always have this pre-multiplication or post-multiplication. This will not turn out to be a diagonal element matrix. Okay. Now, in general, the damping matrix is such that it will not generate a diagonal matrix through this transformation. And so, there are two ways of getting around with this issue. One is to assume that there is there is a decoupling and the diagonal terms are represented. So, this particular term, if we assume that there is a diagonalization that happens, or the product turns out to be only diagonal terms, then we know that this C, the diagonal elements of this matrix would be what? I mean, would it not be for each of these individual equation, let us say Rth equation, this will be the damping coefficient in the Rth mode divided by how much will that be? Each eigenvector would essentially give us upon Mr, isn't it? So, the pre-multiplication and post-multiplication for this, each diagonal element will essentially as a decoupled equations. If we assume the equations as decoupled, then this diagonal element would be almost like will be similar to that Cr upon Mr. Now, we can actually write this as Cr upon the critical damping coefficient and Cc over Mr, and we know that this is equal to zeta r, that is the damping ratio in the Rth mode, and Cc is going to cancel out Mr because this Cc we know that this is 2 Mr omega Pr. So then this particular term turns out to be 2 zeta r Pr. Okay. So, then we say that this matrix, the damping matrix, can be replaced by modal damping ratios, and each of these modal damping ratios will have to be identified. So, each of these diagonal terms will now be quantified through modal damping ratios, and these should be called as the equivalent viscous damping factors. So, all these diagonal elements can be represented as modal damping ratios, and that is the way modal I mean the damping can be represented through modal damping. The other way to write this damping matrix is to say that it is a linear combination of mass and stiffness matrix, sorry, and that basically is again more of a mathematical way of getting decoupled set of equations, because the moment we say that this damping matrix, although is not going to yield a decoupled set of equations, we are approximating it as a linear combination of mass and stiffness matrix, where alpha and beta are constants, unknown coefficients to be determined. The moment you do this representation of the damping matrix, forcing it to be a linear combination of the two, you can then get the decoupling done and solve the equations. Now, this is definitely not going to represent the actual damping in the system. However, it has been also discussed and probably highlighted that the actual damping in the system is very complex, and the parameters of or the damping parameters are not so easy to get. So, when you cannot capture the damping, quantify the damping properly in terms of its value as well as the form, for the sake of getting reasonable vibratory solutions, these are all the getting around with this problem. So, one way is the modal damping, where all the diagonal elements of this product are treated as modal damping ratios, of course 2 into zeta r into pr as the individual diagonal elements of the damping matrix, in a process or in a method of representing the damping through a proportional damping in terms of mass and stiffness. This process or this method is called as a proportional damping, representing the damping as proportional damping. Now, the question is, how do I get this alpha and beta? Okay, how to find this alpha and beta? Now, typically, if we really see this, both of these options or both of these routes are generating the diagonal damping matrix, it then would be quite appropriate to write the equation of the rth term to be like alpha. So, for example, if I convert this equation is going to be an identity matrix here with eta double dot, okay, plus if I pre and post multiply this particular equation, this equation will turn out to be u transpose C into u equal to alpha into u transpose m into u plus beta u transpose k into u, isn't it? Now, if I take this, of course, as we know, is going to generate identity matrix, the product, and this one is going to be beta into the spectral matrix, where all the diagonal elements are the squared natural frequencies. And this one, we can say that this is also going to be a diagonal with the elements as 2 zeta r PR. Now I can write this 2 zeta r PR, the rth row of this matrix equation would be like alpha plus PR square into beta. We have only one equation here, okay, that the unknowns here are alpha and beta, because zeta r PR, these are system parameters. Now even zeta r, you will question as to how do I get that zeta r. So typically what is done is that I can write these as two separate equations from the first row like this, and from the second row right, I have these two equations. Now the two unknowns that I am trying to get, so that I define this matrix to be used later. So what I use is, I use some measured modal damping ratios. These zeta 1 and zeta 2 are the modal damping ratios in the first and second mode. Okay. So through experimental approach means I can get these modal damping ratios experimentally obtained. Okay, I can obtain them experimentally, and I can then use these modal damping ratios to solve these two simultaneous equations to get the values of alpha and beta, and then I can use those constants in the matrix of the damping, and I can then use that in the solution process. Okay. How do I find modal damping ratios? Experimentally. So since we are talking of limited degrees of freedom for the sake of illustration, how do I get the modal damping ratio here? I can excite this system in an appropriate way, so that the modal, I mean the eigenvectors are satisfied. I mean the initial displacement should satisfy the modal first eigenvector relative amplitude ratios, and then release it. Then what will happen? This whole system is going to vibrate in the first mode, and the damping associated with it, if I measure that damping, I will get the modal damping ratios there. But for a practical system, you do not have such discrete a lump parameter model. The actual physical system is quite complex, and it's going to be very difficult for you to initiate the initial condition displacements at each of the points. So then what you do is you excite it the way we do the RAP test. You excite it, and you will then obviously get many modes excited, and the time domain data will have contribution from several modes. And we have seen that general excitation is not going to be exciting only one mode. It may excite at least first few modes quite strongly, and then you can filter this out and then get each frequency response, and then from that time domain data you can find out the damping ratio. You know how to find that using logarithmic decrement. Alternatively, I can excite this with an excitation force, okay, with an excitation force which is at a particular frequency. So because a multi degree of freedom system will have many resonances based on which frequency range you are looking at, but in a typical frequency range you will get several resonances possibly observed, and then half power point method. Using the half power point method, you can find out the damping ratio, which will be specific to this particular mode, assuming that the other modes are quite well separated and they do not contribute to the vibration at this particular resonance. Likewise, one or two resonances you can use for finding out zeta 1, zeta 2, and then that will give you alpha and beta. The only problem is that how does it I mean for higher frequencies and higher modes, will these alpha and beta capture the dynamics properly, because they are based on only first two modal damping ratios, right. So then there are different ways of taking care of this, but we harp on one important assumption here, that we typically do not work in most mechanical system, most rotating mechanical systems. We don't really encountered, except in some cases, frequencies too high so that many modes are crossed over. And if you are working in this particular frequency range, the contribution from higher modes is negligible, right. So they don't contribute much to the response. So it suffices for all practical purposes to use this approach to get alpha and beta. Once you get them, then you can get the decoupled governing equation of motion. Well, with this background, let's relook at how I rewrite this equation of motion. Now I have the mass matrix pre-multiplied, post-multiplied to result into the identity matrix. We all know that eta double dot t, that's the principal coordinate, sorry, we have equations in this principal coordinate, and then this can be then I can write this as 2 zeta r pr as the diagonal matrix for the damping case, and then I have eta dot t, and plus of course you have a spectral matrix here for the stiffness related term, and that's how the governing equation finally trickles down to. Okay, and then because I am interested finally in getting q of t, this is my final objective. With damping included, how do I get q of t, right? And if you recall, in the undamped case, we first figured out how to get the response in the principal coordinate eta, okay, because these equations are decoupled equations in the principal coordinate. We solve it for principal coordinate and then go back to the physical coordinate, right. Let's now pick up the rth equation from this matrix equation, which is all decoupled because this matrix, spectral matrix, is a diagonal one. This we have assumed to be a diagonal one, and now it becomes relatively straightforward from here onwards to focus on one of such decoupled equations. Write them as this eta rt and plus pr square. Make a note that this spectral matrix is a diagonal matrix containing all the squared natural frequencies. These are all eigenvalues. Eta r t equal to 0. Now we start from here, and you will recall that this is the equation, typical equation that you get for a single degree of freedom system. What is the response? The general solution of this governing equation of motion. How do you write that? We wrote this as some coefficient capital X we used to write, right, for a single degree of freedom system. It has to decay over a period of time. This is the exponential decay term which keeps reducing the amplitude every cycle, and of course it has to have an harmonic response. So how do you write that? Now this is not PR, no? PR from the eigenvalue analysis is the undamped natural frequency, right? Here in the damping case, the frequency is going to be a damped natural frequency, right? So to be very precise, I can write this as PDR T minus phi r. Now we all know the expressions of the phase as well as CR. What is CR? Again, let me recall the expression for x of t in the simple single degree of freedom system. This was written as e for omega n t cos omega d t minus phi, right? So this capital X, which is the amplitude, was what? Square root of x naught square plus x naught dot plus zeta omega n x naught over omega d. That is what the amplitude expression was. You may not recollect because this is quite a longish expression as such. Okay. So one way is to use this equation here, writing this as what? Eta r naught square. So this is x naught plus you have eta r dot naught plus zeta r and pr eta r naught over pdr whole square, yeah, and then square root of it. All right. Now things are going to be tricky in the sense that there are too many variables involved here. However, if the damping is for low damping cases, which is most of the times we are all dealing with in the mechanical engineering, for low damping even up to 0.2, which is that way very large value of damping. Okay, for all mechanical system the structural damping is 0.00 something, right? So even for a large damping of this order, the value of the CR or the amplitude will be in error maximum up to 5% maximum, right, for this particular level of damping, for a typical, you know, values of the natural frequencies that I am talking about, typical values. So when the accuracy is tolerated within couple of percent error, you can actually write this in a little simpler form of accounting this as for the undamped case. So eta r naught square plus eta r naught dot upon pr whole square root. Okay, so that can be another alternate way of, you know, keeping things little simplified. You can also accordingly find out the expression for phi r, which we have already seen. It will all come from these two terms. So phi r can also be calculated. Okay, so now from this step onwards, the actual process of getting the physical response will follow the same process as we did for the undamped case. Okay, so what we do here is that we write qt as again summation of all the terms okay, and then you can also write q dot t okay, and now you can use eta r expression so qt at t is equal to 0 turns out like that. right? And then similarly here. Now eta r at t is equal to 0, we have already written eta r to be this, okay, and where Cr itself was written like this. Oh, yeah, I must not have used, yeah, at t is equal to 0. Yeah, that should be fine. So I should be now using this Cr in terms of the initial displacements and velocities in the physical, in the modal coordinates to replace eta rt. And so for eta rt to be written as equal to Cr e to the power minus zeta r p r t cos p d r t minus phi r. So this is what we had. Eta r dot will now be minus zeta r p r c r e to the power minus zeta r p r t cos p d r t minus phi r, and then we have the second term which will appear like minus Cr p d r e to the power minus zeta r p r t sine p d r t minus phi r. And now you substitute your initial conditions at time t is equal to 0. So eta r naught will be Cr cos phi r, and eta r dot at t is equal to 0 turns out to be minus zeta r p r c r cos phi r. All right, and then plus PDR sin phi r, and then CR sin phi r eta r naught minus zeta r p r c r cos phi r. Oh, sorry, this should be divided by PDR. Yeah, right. Now what we do, our actual response is going to be this way, and we again resort to the same approach that you pre-multiply this by UR tilde transpose M Q naught is equal to this is going to give you what, eta r, right? So what is eta r for us? Eta r at t is equal to 0 is Cr cos phi r. This is going to give you Cr cos phi r. Okay, and when you use this equation, please refer to what we did for the undamped case, and then you will find that this is what we got. And similarly here, eta r dot naught is going to be zeta r p r c r cos phi plus c r p d r sin phi r, because this is the expression that we have for eta r dot at time t is equal to 0. Okay. Now you can replace CR cos phi r in this equation to generate the expression for CR sin phi r to be 1 over PR PDR into UR tilde transpose M Q. Okay, and then minus zeta R PR CR cos phi r. Now CR cos phi r itself is UR tilde transpose M and Q naught. Okay, that's so. Let me rewrite this expression CR sin phi r. That's how you get CR sin phi r. Okay, and now finally, if you want to use finally this expression, okay, eta r as a function of time is going to be e to the power minus zeta r p r t c r cos p d r t cos phi r plus sin p d r t sin phi r. Okay, and now you can replace CR cos phi r from this expression and CR sin phi r from this expression. So they are again all in terms of modal mass normalized modal vectors, the system matrices and the initial physical condition. Okay, so those are the things that can be now replaced here, so that you have CR cos phi r replaced like U R tilde transpose M Q naught and t is equal to 0, that is CR cos phi r, and then cos PDRT. Mind you, PDRT or PDR actually is PR into 1 minus zeta r square half. Okay, that is your damped natural frequency. So this is one time function, and then plus you have CR sin phi r, which is given by this expression, which can be now written as 1 over PDR and CR sin phi r. Yeah, so this is multiplied by UR tilde transpose M Q naught dot minus zeta R PR UR tilde transpose M Q naught. Yeah, here it is. Oh, sorry. Yeah, this, and then multiplied by sin PD R T. That's the overall matrix that you get, the expression that you get. And once you do that, we have one last thing to do is to write Qt in the form of this matrix equation to n, and you can replace eta RT completely here, which I am not going to write, and it is simply going to be multiplied by URT. That's basically is your final response of a damped vibratory system. So it looks little longish and apparently complicated, but if you know things, I mean, this is all very simple. These are all ultimately turns out to be some simple elements or vectors of the size depending on your degrees of freedom. Okay, so you prescribe the initial displacement and velocities, and many times it so happens that you either give only initial displacement or initial velocity. So one of those terms are anyway going to go off, you know, that will be 0. So this is a more generic expression, and then you can find out the response. Once this is properly put in place, it really does not matter whether your number of degrees of freedom are 5, 10, 100, 1000, 10,000, 1 lakh, whatever. Okay, it simply boils down to matrix multiplication. That's it.
Okay, let us take a brief recap of the whole process of modal analysis for a damped vibratory system to get its free vibration response.
Now, we have already discussed this. So, we derived these expressions of how the modal damping ratios are connected to the constants, arbitrary constants alpha and beta for a proportional damping assumption, and how by assuming them to be given equal to the diagonal elements of the damping matrix, how we can decouple the system effectively by assuming the diagonal elements to be given by these terms. So, this is something which we already discussed. So, apart from diagonalizing the inertia related term, that is the mass times acceleration and stiffness times the response, both these matrices were shown to get diagonalized because of the modal transformation. And in this particular case, we have seen that although C strictly will not get diagonalized even if you pre and post multiply with the orthonormal modal matrix, but we as an assumption treat that as an approximation, we assume that with that multiplication the matrix elements are such that the diagonal elements can be treated as 2 zeta or PR. Okay. And that we have shown that if we take those elements, diagonal elements, they are like C over M. Okay. And we show that C over M turns out to be 2 zeta PR for a single degree of freedom system we have shown, and here through the diagonalization we know that each equation is going to be almost similar to your single degree of freedom system. So, once they are diagonalized and decoupled that way, then each equation can be written in this form. So, rth row equation turns out to be this, and the standard solution for such a single degree of freedom system is given in a standard form like this. That also we discussed that it is going to be CR e to the power minus zeta r PR t cos PD RT minus phi r. Okay. And this can also be written in a separate way by expanding this. You can see that it is given by this expression. What we are now supposed to figure out is how to get these two unknown constants, the constant CR and the phase phi r. Now, if you put the initial conditions at t is equal to 0, eta r naught and eta r dot naught, quite similar to our undamped case, they can be shown as you can see here. We will not get into the details. These have been already discussed in our foregone lecture.
now by substituting this CR and phi r, one can then substitute for these constants by again making use of the initial conditions in the physical coordinate. So, these equations now we are quite familiar with. So, eta r naught is expressed in terms of the q naught and q dot naught, which if we substitute back into this equation, we can finally get an expression in the physical in the principal coordinates it is given by this. So, in the principal coordinate by substituting for CR and phi r, this is what we finally get the equation in the principal coordinates. Now, in terms of the initial conditions in the physical coordinate, and then when you substitute eta r t in the expression of the modal expansion, where qt was represented as summation series involving modal vectors, and that way this is the way the final expression turns out. If you have understood the undamped case, you simply have to extrapolate this to damped case. The only thing that is happening is some few more terms are getting involved, but the basic philosophy remains exactly identical. Now, again you can note here the physical response, all these are quite straightforward and known. You know all your eigenvectors, you can find out your individual damped eigenvalues or damped natural frequencies from the eigenvalue analysis. You can find out what is PR, and by using the modal damping ratios zeta r, you can find out all the parameters which are involved in this expression. Okay. So, these are all your this is q dot naught, that is the initial velocity. Practically everything in the expression is well defined and known. What you need to do is to substitute appropriate t value to get the q value at that time t. Okay. Now comes the last important part of how we use or accommodate the external force on the right hand side to evaluate the response to any excitation. The excitation can be harmonic, it can be periodic, it can be arbitrary or transient excitation. This is the standard equation. Again I am coming back to this. Before we go ahead, I thought it would be appropriate to simply say that if I use the assumed solution in the form of q e to the power j omega t, right, meaning that I have some external q e to the power j omega t, and of course you can add some phase also. That basically is the assumed response for this kind of an external excitation, provided of course if f of t itself is a harmonic function of time. So, if I use f naught e to the power j omega t, now in each of these cases these are all vectors. So, f naught means f naught at degree of freedom 1, degree of freedom 2 and so on, but essentially they represent the same thing. If you do that, what finally you will end up with is this mass matrix, okay, times omega square, if that is the only frequency involved, which is a valid assumption, because we start with a harmonic excitation case and then use the superposition approach to get the responses due to several excitations simultaneously happening. Plus I can write this as j omega into C matrix plus this K matrix, and then this entire term multiplied by Q, which is the response amplitude, is equal to your F vector. Now, if I want to know, see, basically to find out the response at any instant of time, I need this amplitude. Okay. Once I get this amplitude vector, what is the response at degree of freedom 1, what is the response at degree of freedom 2, response amplitude. Once I get, I simply have to multiply with the time harmonic time function to get the dynamic response. But the first thing is getting capital X or capital X1, capital X2, capital X3 and so on. So, if I want to know what is the response amplitude at each of those n cross 1 degree of freedom, n degree of freedom, then what can I do? this entire matrix, which I can call as a dynamic matrix, I will invert this dynamic matrix and multiply it with the external force vector. Can I do that? This also is one way of finding out the response. Okay, I invert this matrix, okay, and I get the response, because once I get q is already defined as a function of time, sorry, as a function of time, qt is already defined, because that is basically q e to the power j omega t minus phi. Omega is known, I can find out phi, okay. That phi anyway is going to appear here because of the presence of j omega c term. That is going to be a complex quantity which I can get its absolute value and the corresponding phase, that is not a problem. What is the issue involved here? Because this is quite straightforward, right? Why do I need to now follow the modal analysis approach of getting the response? So, suppose I am interested in getting the value of q as a function of, now I might be interested in plotting the frequency response behavior. So, n degree of freedom system, I will have many resonances at all frequencies, okay. What this is going to give me is for a particular frequency of excitation, what is the q value, right. For some other frequency I will get another one. So, this is omega 2, this is omega 1, countless number of omegas, right. If I change the excitation frequency, is this matrix the same? It is not, because this is dependent on the frequency of excitation, the frequency involved. So, in the inversion process, I will have to do this inversion every time for every new frequency of excitation. So, getting this entire response sort of a response spectrum, getting the response values at all the frequencies of interest, each time I have to invert this entire matrix. And imagine that this matrix is for, let us say, 5000 degrees of freedom, right. Every inversion is going to take a hell of a time, right. So, this method, which is called as a matrix inversion method of finding out the dynamic response of several degrees of freedom, multi degree of freedom system, is computationally not advisable. It is going to be very expensive process. That is why we have to find an alternative which is computationally more elegant and inexpensive. So, we resort to the same, we assume the system to be having symmetric stiffness, mass and damping matrices. That is an assumption, of course, because then only our orthogonality will work. So, pre-multiplying, post-multiplying, converting into our principal coordinates etas, you get all of these. Now, in this case, pre-multiplying by the transpose of the normalized modal matrix will generate generalized excitation force, okay. These are generalized forces NT. So, Rth equation will give you an equation similar to our single degree of freedom forced vibration equation, mx double dot plus cx dot plus kx equal to f of ft, right, same as that. And it is quite possible again to show that the response to this is given by this expression, okay. Same way as we did it for a single degree of freedom system, x of t was given as f naught by k divided by this expression. Again you can see this looks quite familiar to you now that you have learned single degree of freedom system, okay, of course. And of course, the numerator will get changed to to this expression, which you can show that it is true considering the fact that this is in the principal coordinate eta r. The phase phi in the rth mode is again similar. You must have seen 2 zeta r upon 1 minus r square. Once the response in the principal coordinates is obtained, you can now convert it back to the physical coordinates. The process again remains the same, you use the same expansion. Okay. So, that process is again not discussed here, but once you know how the principal coordinates is obtained, getting the original, I mean the physical coordinate response is quite straightforward. If it is not a harmonic excitation, if it is an arbitrary excitation, we have seen how Duhamel's integral or a convolution integral was used in a single degree of freedom system. You remember that? How much was it? So, how was it? X of t was written as 1 upon omega n 0 to t, and f tau sine for an undamped case it would be sine omega n t minus tau d tau, right. That is how we wrote for a undamped case. If there is a damping, then of course the exponential term will appear in addition to that, and yeah. So, this is basically what we had already seen for a undamped case. So, in a modal coordinates eta r for an arbitrary excitation force where the force itself is varying, arbitrarily as a function of time. So, this basically is eta r tau. So, when you do that, that is the way the response in the modal coordinates, very similar to what we have seen in the single degree of freedom system. And that is precisely the reason why we learn single degree of freedom system first, learn it thoroughly, get all the insights into the phenomena, and then we are seeing how it just simply extrapolates to a multi degree of freedom system, thanks to of course the modal transformation. But we know that it is not, so when we want to add to the initial conditions, then similar kind of initial conditions will also get added up, right. So, even you must understand that this is only the response due to steady state condition, that means steady state response, but actual solution of this equation, if you recollect, it has transient part and a steady state solution. So, the steady state solution will be obtained from this expression, okay, but the initial transient, because of initial conditions, will have to be included if you want to express the entire total response. And of course, we all know that given the amount of damping that typically a vibratory system has, this particular part, which is transient part, is going to soon die out, right, and then you are left with only the response to the steady state or a force, the harmonic excitation or an arbitrary excitation that is impressed on the system. But mathematically this is the complete response, and once eta RT is expressed like this, in place of this convolution integral, in place of this convolution integral, you may have this part replacing this if it is a harmonic excitation case. This part is basically based on your initial conditions. This of course, even in the case of a harmonic solution, even if there is no explicit expressed initial conditions, we will have to theoretically write it this way and then see which part to be included and not. So, this is how even for an external excitation force, modal analysis can simplify the solution process quite well. Now, the question again is that how do you get rid of, how do you account for this integral sign? How do you, so now you may notice that if this eta RT, if it is like can be expressed in the form of a mathematical function, then the integral can be solved and then you get a closed form mathematical equation which you can solve for each of the time. Otherwise, you will have to use numerical method to find out or get the response value. Okay. So, eta or tau, if you can express that in terms of some mathematical expression which can be integrated, then this entire term you can get in the form of an expression, mathematical expression. Once you get that mathematical expression, then getting qt at any instant of time is not going to be a problem. Okay, in today's lecture we discussed how the response of a typical damped multi-degree of freedom system is obtained using modal analysis approach, and in the process we discussed how some approximations and assumptions are necessary to generate decoupled governing equations of motion for a damped multi-degree of freedom system. The damping matrix as such is a coupled one, but we have to use some assumptions in decoupling them. In that context, we understood the concept behind proportional damping, and that helped us in generating equations which could be solved efficiently. In continuation, we also extended the free vibration analysis process using modal analysis to understand how the forced vibration response can also be obtained. These are the review questions based on the discussion we had today. And these are the answers to the questions.